Test, test, sound, sound. 1, 2, 3. Okay, lights, camera, action. All ready to go. All good? Oh no. Oh no. I think, is there an input going in? 1, 2, that's, it's number 2, right?
Mm-hmm.
Oh, yes, they've disconnected HDMI out. Goodness, guys. Okay, should come back. Good morning, everybody. Welcome to the voter-mandated session of Chem 1. Yesterday, we were talking about vapor pressure, and we were talking about it in the context of the equilibrium between liquid water and gaseous water, and all the ways we kind of understand that now. So we understand a great deal about this equilibrium, and we had started to look at it on a phase diagram. So here I've plotted the pressure versus the temperature, and we'll review what we did at the end of class last time, because that brings together so much of the thermodynamics, and now this idea of a phase diagram plotting in pressure and temperature space. And we've also plotted in pressure volume space. We've been able to draw isotherms in both spaces. And we can now start associating our isotherms with values of K, because we understand K is a constant at a constant temperature. So we know each temperature here corresponds to a different value of K, and we can read them off. They are this line where the liquid and vapor are in equilibrium. So we talked about one point in particular, of course, the boiling point of water. It's called a normal boiling point of water, 100 degrees Celsius, 373 K, and 1 atmosphere of water vapor pressure. So if we have 1 atmosphere of water vapor pressure, that, as we also know, corresponds to what we call the standard state. Standard states are 1 atmosphere or 1 molar concentrations. The pure liquids and solids are present. They don't have a concentration. They don't appear in the equilibrium expressions. So the equilibrium expression we know for this is simply K, and we'll give it a specific temperature, is the partial pressure of the water vapor. That's how we write the equilibrium constant. The pure liquid doesn't appear. So K is just a pressure, and that allows us to find K on a pressure temperature diagram. So we're plotting vapor pressure or K here, the same thing. So if we look at, though, a state where Q, where the pressure is 1 atmosphere, that is the standard state. So all along this line, you're in the standard state. And you can be in the standard state in any temperature. In particular, if we're here at 100 degrees, the standard state, 1 atmosphere of water vapor, then Q is 1, K is 1 in this situation. Because 100 degrees, 1 atmosphere is the equilibrium condition. We are on that line at 100 degrees C and 1 atmosphere of vapor pressure. So this is just a kind of a coincidental case where the standard state free energy difference at 100 degrees is 0. So Ks are rarely 1, but in this case, it is 1 because we're talking about K is just simply the partial pressure of the gaseous water, and we can arrange that it be 1. One way to do it is take water, liquid, to 100 degrees, and the vapor pressure, K, will be 1. Delta G of that reaction is also 0. This is in equilibrium at 100 K. So the free energy difference between the products, 1 atmosphere of gas and liquid water at 100 degrees C, the free energy difference between those is 0. And that's reflected in both that that's the standard state, happens to be. It just, this delta G of this reaction is the standard state. So they are all in equilibrium. So those are 0. It's not going to change from that state unless we change the temperature. Water and gas in equilibrium everywhere along that line. But we often talk about 25 degrees C. We talk about room temperature, but we can still talk about the standard state at room temperature. So let's go to the standard state at 25. And now we have this feeling from our phase diagram that it's the liquid that's favored under these conditions. So we're getting 2 sources of input. If we have a 1 atmosphere of vapor at 25 degrees C, it's the liquid phase that is favored. And we see that in our phase diagram, but we also remember that we can say, oh, I'll just read what K is at that temperature. I can read K at that temperature, or the standard vapor pressure at that temperature off the curve. And we know, we've seen it 100 times now, that that's 3/100ths of an atmosphere. So that is the vapor pressure, or K, at 25 degrees C. It's not 1 anymore. So there's K. We are not there, though. We're saying we're up here at the standard state. So we're saying our conditions, and of course, the conditions that you're talking about, the conditions of the reaction, are where you define Q. The conditions at equilibrium are K. And we are away from equilibrium, and you can see that graphically here. That's equilibrium. We're up here. The liquid should be favored. We know that from the phase diagram, but we also know that because K here is less than 1. And when K is less than 1, that means reactants are favored, and the reactant is the liquid water. So standard state, Q is 1 in this case, but that's much bigger than K. So that also tells us Q bigger than K. I'm going to go back towards reactants. So all that information is the same. The standard state free energy difference here is positive because K is less than 1. K is a constant, and delta G standard is a constant at a different temperature, but they can be different values at different temperatures. So here, delta G0 is bigger than 0. And that also tells us that that's a positive free energy difference. That's not spontaneous as written. The reactants are favored at equilibrium. All those things are telling us the same thing. And we can get the liquid is favored here, and the free energy of the reaction under those conditions is the same. It's greater than 0. We've had a situation where there's 1 atmosphere. Q is greater than K. Free energy under those conditions is, I'll go back towards the reactants. So there's a third point we can look at with all those variables. If we are at this point, so we drop the pressure of the water vapor from 1 to 3/100ths of an atmosphere, then Q, I've dropped it to 3/100ths of an atmosphere, is K, 3/100ths of an atmosphere. I'm on that line. That's the equilibrium line. The standard state free energy difference is still RT ln Q. So that number is still greater than 0 because that always refers to this. If I put that 0, that refers to this state, regardless of where I actually am. That 0 means I'm talking about this state. So those numbers are the same, but I'm at equilibrium here. If I have actually 3/100ths of an atmosphere, then that is at equilibrium. The standard state free energy difference, the instantaneous, the reaction standard state free energy under those conditions is 0. We are at equilibrium. So equilibrium at 25 degrees C, those are the conditions. Equilibrium at 100 degrees C, equilibrium is not achieved off that line, and the liquid is the favored state. So that beautifully, I think, encapsulates so much of what we understand from phase diagrams, from the phases of matter, the transitions between them, the lines on the phase diagram corresponding to values of K, equilibrium values of the, and we could do it with the solid and the liquid, or the solid and the gas. We could do it for the sublimation or the condensation reactions or vaporization reactions. So beautiful summary. So let's ask then, I have 3 lines plotted here, and these are isotherms. That is, this temperature, this is the temperature axis. So the temperature is constant along those. So we could transfer those to a PV plot if we wanted. That's a pressure temperature plot. So we're looking at a phase diagram, which is the 373 isotherm for water, A, B, or C. So think about that for a second. And we will take a vote on that. All right. I'm Okay, we're back. Let's see what you're thinking. Give you a minute to push a button. Oh, you can't because I turned it off already. Let's see what you were thinking. Many of us thinking B. This temperature here is 373. That's getting close to half of us. I do not agree with the B's. So this is labeled as the critical temperature. And beyond that, there are not two phases anymore. And that is where two phases become indistinguishable. We saw that last time when we took supercritical carbon dioxide, and we saw that instead of being able to see the two phases, the liquid phase and a line, saying there's the condensed phase and the gas phase above it, that line literally went away. The line between the two phases went away as we went supercritical and we had only one phase. It was the same density as the liquid, but it behaved like a gas and filled the whole container. A very strange state of matter. And I think intuitively, it's not a state of matter that we see very often. I think at 373, that's 100 degrees Celsius. That's the boiling point of water. We see both phases, the liquid, and we see the line. There's the water, liquid, boiling, and there's differentiation between them. So this is where that would start to disappear. Above it, certainly not. You need to have a liquid water equilibrium point somewhere on your isotherm if you're at 373 K. There has to be that point where liquid and gas are in equilibrium. So that point. Critical temperatures you should, like I said, they're odd things. We don't see them very often. It's a weird combination of temperatures and pressures. For carbon dioxide, we saw that critical temperature was around 32 Celsius, I think it was. So it's, just above room temperature. So it's just a hot day, but the pressure was 1,000 PSI. So even though the critical temperature wasn't very high, the pressure was just outrageous and made it a condition we wouldn't see very often. For water, it is the critical temperature is extremely high, and you would predict that. That's kind of something I might be able to ask you. You would predict that because that says there's this change in kinetic energy and intermolecular forces. It's a very high temperature you had to go to. I think it's 650-ish Kelvin, so really crazy high temperature. And the pressure is also 200 atmospheres. So very odd conditions, that point right there. I could ask you, this is a fair exam question, once you've established that is the 373 isotherm, so we can, we'll just stay on this. Well, this is okay. We can go to this one because this is just an expansion of that. There it is. This is, so you had the answer on the last slide. That is the 373. I had written it in Celsius, but this is 373 K here. And you can see it's below the critical temperature. That's line A that we just had in the last slide. We had A, and then we had B isotherm right at the critical temperature, and then we had C isotherm above the critical temperature. So it would be fair on the exam after I said, okay, you've identified this as the 373 K isotherm, it would be fair for water for me to ask you what that pressure is, because you should know the normal boiling points the vapor pressure, whatever whatever the compound is, the normal boiling point is defined as when the vapor pressure is 1 atmosphere. That's the point where it has enough kinetic energy, enough free energy, is really what it is, to push the atmosphere back and to boil, to become a gas. So that is 1 atmosphere. So I could have asked you not only is that which one is 373, but what is the pressure at that point? So it's all 373. It's an isotherm, but different pressures on that isotherm. Brilliant. I also might ask you, what would it look like if it were pressure volume? So we have A, B, C isotherms. The C isotherm is easy to plot because at the C isotherm, PV is a constant. We've talked about that. It behaves like one phase, like a gas. P times V is a constant out there at C. At B, we're at the critical temperature. A, we're below the critical temperature. So what do these isotherms look like in for real gases? You see the condensation. Here is where you have the gas changing to the liquid. And the gas is changing to the liquid, so the volume changes dramatically at constant pressure. So the volume is changing dramatically because the particles are turning into liquid. So there's that dramatic change. So you should be able to plot that. And then B is the critical temperature. And that's where you just start to see that real behavior involved. Above that, you don't see it. Below that, you do see real behavior. And I'm just real quotation marks. It's all real. But ideal gas and real gas kind of behavior. So that is a brilliant summary of everything that you might see on the exam on Monday. We have my puppy here, Arrow. Do you want us to come and say hi? Come here. Good boy, sit. Good boy, wait. Good boy. This is Arrow. Say hi to Kim One, Arrow. He's a mini Australian Shepherd. He's 9 months old, and he's beautiful. Blue eyes and beautiful color. He's 9-month. Arrow is for aerodynamic. His full name is Aerodynamic. Are you eating the microphone? Good boy. I know, I love you too. So let's continue of our discussion here. We'll put those equilibrium states in there. So as we said, that's the boiling isotherm. So the answer to this chem quiz is A. So let me ask you this. I'm going to take an evacuated flask, inject liquid water into it. So it's a 22-liter flask here. I'm going to inject 20 grams of water into the evacuated flask at 25 degrees C. The question is, what is in the flask after equilibrium is reached? Does it all turn into a gas? Is there a mixture, or is it impossible to tell? Is there not enough information to tell that that is what happens? So let's think about that for a second. And take a vote. Okay, let's come back together and see what you're thinking. We had a good discussion here in the classroom, such as it is, the office. Well over half of us think there'll be a liquid and a gas. And I agree with you. I wonder if your reasoning was correct. So let's go through this one. So the vapor pressure at 25 degrees C is 3/100 of an atmosphere. I've said that so many times. I don't expect you to memorize it. I will give it to you on an exam. But we said it so many times that I think you probably remember that that's what it is. So that is the H2O liquid in equilibrium with H2O gas. That's the equilibrium constant. That is the pressure of water at equilibrium. You're not at equilibrium. You inject it into a flask that's evacuated. So you inject some water in there, and water will evaporate until what? It reaches equilibrium at 25 degrees C. So it will evaporate until this pressure is 0.03 atmospheres. The question is, when that gets to 0.03 atmospheres, have you used up all your water? So you have to say, well, how much is that? The flask pressure is going to be 3/100 of an atmosphere. 22 liters and 25 degrees C and 1 atmosphere, you should recognize as standard temperature and pressure. So we told you it was standard temperature and standard pressure. If a gas were going to form there and fill the whole container, it would take 1 mole of gas to fill the entire container. We have more than a mole of gas. We have 20 grams of water. 20 grams of water is more than a mole. A mole is 18 grams. So even if the pressure were to get to 1 atmosphere, you wouldn't use up all your water. You'd only use up 18 grams of your water, and you'd have 2 grams of water left. It does not get to 1. It gets to 0.3 and stops. So this is another one of those cases where you might have a misconception about what a vacuum does. Does a vacuum make everything evaporate infinitely, just the whole thing just vaporize? No. Remember, the partial pressure of water is what you're talking about. The partial pressure of water achieved in there is 0.03. It happens to be the only gas. So the total pressure is also 0.03. But the liquid water cannot add any more particles to the system. Remember, gas particles don't know that any other gas particles are there. So they didn't even know it was a vacuum to start with. All the water said is, I'm here, my pressure above me is 0, I'm all liquid, I have to evaporate until my vapor pressure, I have enough water particles in the flask that my pressure comes to 0.03 atmospheres. So that is a good fundamental exercise to go through. What happens, and dispel all your bad misconceptions about vacuums. Vacuums don't do anything. People have this impression from all our science fiction that the vacuum has to do something. No. The substances do something, and we know what they do. They come to equilibrium, and when they come to equilibrium, the partial pressure of that water vapor is going to be 3 atmosphere, or 0.03, 3/100 of an atmosphere. So yes, we can get to our 3/100 of an atmosphere and use up just a tiny fraction. So in the end, most of your water is still a liquid in the bottom of that evacuated flask. Even though it's a vacuum, most of your water is still liquid. Okay, so let's do this. Let's just do kind of a back of the envelope calculation. What's the approximate volume of 1,000 grams of air at sea level, 1 atmosphere and 298 K? So here you actually have to scratch out some numbers. So so you don't have to look at a periodic table. I will remind you, if I can. I suck at remembering the periodic table, as you know. I resisted. But the molar mass of nitrogen, I believe, is 14, and the molar mass of oxygen is 16. So that will help you determine. And we're just doing approximate. Just give me about the number here. So you don't have to do any, maybe you don't even have to take the calculator out. And you can see I'm giving you factors of 10 here. So you can probably get within a factor of 10 without doing the whole calculation. So let's start that. Go ahead and do the calculation as if you were taking the exam right now. Fair exam question. Absolutely. It's just a PV equals nRT. Okay, take a stab at this one if you haven't gone through all the calculations. But yes, treat this like an exam question. This is perfectly valid. It's a straightforward thing. Let's see what you're thinking. We're spread out a little bit, but over a third of us, coincidentally, think 800 liters, and I agree with the 800 liter people. Why is that? Well, you can sketch this out in more detail. I did this kind of calculation. We had a mixture of N2. We had a mixture of N2 at 80% and O2 at 20%. So you could do something like 800 of those 1,000 grams is use mass 28 for the nitrogen. So convert grams to moles. And 200 of them are oxygen at 32 grams per mole. You could have done that. But you could do the least common denominator thing. And this is approximately equal to 1,000 over 30, you know, kind of the average of those and the sum of those. Not exact, but we're trying to get within a factor of 10. So we're going to get there. So that's what I've done here. I've just kind of fudged 1,000 grams, an effective molar mass of the mixture of 30 grams. So something like 30-ish moles. And then once you're at 30 moles, you need to get to the volume. And you now know N, R, and T, because I told you it was 298 K. So put those in. 33 moles, 0.082 is R, 298, and 1 atmosphere. And I was just talking with Sophia here, how important it is, put your units in. I haven't done it here, but I'm going to do it to emphasize. I saying something like 33 moles, and I'm going to put R in there, 0.082, and put the units of R, liter times atmosphere per mole Kelvin. Get those units in there times 298 Kelvin. Everything divided by 1 atmosphere of pressure. And then make sure that all your units, atmospheres cancel, moles cancel, Kelvin cancel, make sure that the unit you're left with is the unit you want, volume. So that will always check your, help you check your math if you're dimensional. It's called dimensional analysis. That's a little too highfalutin, but that'll get you the liters, and that's about 800. And you don't even have to do the math here. This number is about 0.1, and 30 times 300, you need something like 1/10 of that. So that's going to be a big number. Okay. Beautiful. Good practice. So let me ask you this then. How many grams of water are in 1,000 grams of air at equilibrium at sea level? So the air pressure is 1 atmosphere, the temperature. So we know now, essentially, we'll work through this one together. We just calculated what this volume is. So the volume, you take a chunk of air until you get 1,000 grams. How big a chunk of air do you have to carve out? You have to carve out about 800 liters to get your 1,000 grams of air. So after you carve out that chunk, you have to say, well, in that chunk, that 800 liters, how much water vapor is there if there's water present, if there's liquid water present at 298? Well, if there's liquid water present at 298, the partial pressure of the gaseous water must be 0.3. I don't care what else is going on. If this is there and the temperature is 298, then this is there at 0.03 atmospheres of pressure. Period. Take that to the bank. You don't care. Remember, equilibria don't care what other equilibria are happening in the system. Well, they do care to the extent that they all become equilibrium together. And we're going to talk about that a lot shortly when we talk about acids and bases, where we talk about many equilibria happening simultaneously. But we talked about it when we talked about equilibria. In this case, this is the only important equilibrium happening. There aren't a lot of chemical reactions or anything else happening. There's just this solid vapor equilibrium occurring. So the pressure in this 800 liters of liquid water is going to have to be 0.03. Okay, so I can do that. We're interested in the mass of the water there, but we can get the moles of the water. The moles of the water is PV equals over RT. This has to be the pressure in atmospheres. We know the volume of 1,000 grams of air. There's R. So we have our P times V over R times T. There's our temperature. That turns out to be about 1. Okay. So how many grams of water are there in 1,000 grams of water of air at sea level? Around 20. Okay. That would be saturated air. That means I'm at the equilibrium point. So now we're at the point where we can talk a little bit about the weather. If you ask a meteorologist, a real meteorologist, what the most important parameter is to predict and understand the conditions of weather, they will tell you the moisture content of the air. That is the most important factor. It'll tell you whether it's raining, whether it's foggy, whether it's dry. The temperature is a factor, but the moisture content of the air usually has that temperature, some information there. One reason the moisture content is so important is that that reaction, H2O liquid going to H2O gas, that's a 44 kilojoule per mole process. So that process is a very energetic process. So if that's going to be forced to happen, that's going to influence what happens in the weather. And the idea of adiabatic and expansions and contractions are going to come into play. So all the things we kind of have looked at are going to come into play when we talk about the weather. So we now know that saturated air, we can start right here. Oh, I think I have it. I think it's in this animation. Saturated air, if we have equilibrium between the water vapor and the liquid water, we know those partial pressures. So let's look at a couple temperatures, partial pressures of water, the actual vapor pressure, and what we're going to call the relative humidity. That's a number you hear very often. So at 25 degrees C, the equilibrium condition is 0.03 of an atmosphere, and we've figured that out to be about 20 grams of water per kilogram of air. Not particularly useful, but that's how meteorologists do it. That means, so here's my 1,000 or my 800 liter chunk of air, and there's enough water vapor, those gray particles, to make 0.03 of an atmosphere of water vapor pressure. There's also the pressure from the N2 and the O2. That's what gets us to about 1 atmosphere. But the water vapor partial pressure is 0.03 if I'm at equilibrium and I'm saturated. But we frequently are not. We call that 100% humidity if we are saturated, 100% relative humidity. So this will be our baseline condition in parentheses here. This is Q. We're saying if that's the condition we have, but that's also K because we know K. And so what this relative humidity is it's a Q over K times 100. So the ratio of Q to K is 1 times 100 is the relative humidity. And that's an equilibrium at 25 degrees C. But I think we're seldom there. If we were there and we're there at sea level, the air would be saturated with the vapor. We would start to see liquid water condensing, and the liquid water would condense among the air. There would be fog or rain or clouds under those conditions. So right now in Berkeley, where many of you haven't come to Berkeley yet, but you'll soon find out when you get here, we're there a lot. We're totally fogged in all the time. So today we already have sunshine. But across the country, say you're in Minnesota or something, let's say you're at 25 degrees C, so you're at kind of a comfortable temperature, but the relative humidity is not 100%. The water, when the relative humidity is 100%, we say that feels hotter. It's a wet heat. That's because any water that you sweat out, how does that sweating cool you off? Well, it cools you off by some of that sweat evaporating. And that's endothermic. That removes heat from your body. But what partial pressure can the sweat on your body achieve at 25 degrees C? It can only achieve 0.03 of an atmosphere. And if the air is already 0.03 of an atmosphere, then the water comes out of your skin, but there's 0.03 of atmosphere there. It's already at equilibrium and it can't evaporate. So it's harder to cool ourselves at 100% humidity. Luckily, our body is more than 25 degrees C, so a little of it does evaporate. But so in the little tiny micro state of our body, very close around our body, a little does evaporate because our skin is at 60, 70 Fahrenheit. So let's just take a number you frequently see, 30% relative humidity. You go up, you turn on the TV or you're listening to the radio in the morning, and the weather person says 30% relative humidity. Or they might give you the dew point. That we'll talk about what that is. No, I don't know why they give you the dew point, because absolutely no one knows what that means. Maybe I won't even tell you because you don't care either. So, but that means Q over K must be 0.3 if I'm at 30% humidity. But I know K at that temperature, so I can back out what Q is. And you can see 0.3 over 0.03 is that 0.009, around 6 grams per kilogram of air. So that's Q. That is the partial pressure. The partial pressure of water when we're at 30% humidity is lower than the equilibrium pressure. That's what this is telling you. I'm at 30% of the equilibrium pressure. So that's a condition, and that's a sea level condition. And I've drawn this chart here of the relative altitude, the surface of the Earth, and going up to 5,000 feet. So let's say at this point, the liquid is favored, as we know. So I don't know why we have done that. That's a typo. At that point, the gas is favored. So as I go up in the atmosphere, what happens? Well, the pressure decreases as I go up in atmosphere. So I'm at a relatively low pressure high above the atmosphere and a higher pressure near the surface. And then we know that pressure is around 1 atmosphere. It's what we define it to be. And up here, when we get to 5,000 feet, you know, if you're flying on an airplane up at 5,000 feet or, 30,000 feet, as you do on a commercial airliner, you're at very low pressure. And you have seen the movies where the exit door flies open and people are blown out from the high pressure of the cabin to the low pressure of the atmosphere around them. So low pressure up here, quite low pressure. So if this mass of air, if this 800 liters of air rises up through the atmosphere, if you imagine that happening, that would expand against the lower pressure. And as it expands against the lower pressure, what happens? Well, it's an adiabatic process. There's no place to get heat from, essentially. You're all air. So you expand, and as you expand adiabatically, you're expanding, you're pushing back the rest of the atmosphere, you're doing work. What happens to your temperature? It goes down. You have to use some of your energy to push back the atmosphere. Your temperature drops. And that's what we're seeing here. Lower temperatures as we go up in the atmosphere. And that is true too. You may even experience this if you just go up into the mountains. The temperature generally lower. And we're going to see that clouds form. And why is that? If this gas rose up, it's 30% humidity. If that gas rose up and experienced that adiabatic cooling until the temperature dropped to around 5 degrees Celsius, and we still have this amount of water in our system per kilogram, here, when we get up to 5 degrees C, the vapor pressure, K, is 0.09, 9 thousandths of an atmosphere. So when we get up there, Q and K are equal. Again, we're back to 100% humidity when we get here. 100% humidity means I see the water vapor. And there's no surface for it to condense on, so it doesn't condense into a puddle. We see it as clouds. We see the liquid water suspended in the air. That's a cloud. Okay, so we call this the condensation level. Adiabatic cooling, when you've cooled enough that you've reached equilibrium for the relative humidity that you have, then you get a condensation. That's why clouds generally form on a warm summer day. You can start out perfectly blue and clouds will form on a warm summer day. As that air rises, that moist air condenses. The water eventually condenses from the air. You can make it happen dramatically. So let's look at a dramatic adiabatic expansion. So this guy is making the pressure inside this flask with a little water on the bottom of it super high, crazy high, so way beyond an atmosphere. And what he's going to do is release it suddenly. That's an adiabatic expansion. Happened fast. And the water vapor in there instantly condensed and formed a cloud. So he just formed a cloud in a bottle by doing the adiabatic expansion by taking the cap off of it. So beautiful demonstration. If we were in the lecture hall, we would do that demonstration for you, and I would make a cloud. I would be Thor, the god of thunder, and make a cloud. And you know, when you think of Thor, the god of thunder, you think of, you know, Chris Hemsworth, and I think that probably makes you think of me too. That guy, he's like stupid handsome. I mean, photoshopped handsome all the time. You don't know whether to love him or to hate him. How do I get this to go back to the PowerPoint? So we have a good understanding of where clouds form and what the weather, how weather affects us. Not everybody gets that. Adiabatic processes, not everybody gets it. And you guys have struggled with it. So this is going to make you feel better. This guy probably has a degree in meteorology. But this newscast happened a year ago, and I was so incensed by it that I took a picture of the television. This guy is trying to explain why we have increased fire danger, these hot, dry breezes that cause the big fire danger. This was back 2 years ago when all of California was burning. And it's exacerbated by these hot breezes. And he said dry air travels down from the mountains in California. That's the opposite process. Okay? So he said, well, air drops down, it's compressed. This adds air friction to the air molecules, which heats and dries out the air. What? No, it's adiabatic compression. The atmosphere is doing work on a volume of gas, and it is heating up. So this guy should have paid better attention, embarrassed himself on television. If you were to add, it's even the opposite thing. Think about it. If you were to add friction somehow between the molecules, what would that cause? What would happen to the collisions? Every time you collided, what would happen? They'd slow down a little bit. So if the gas particles slow down a little bit, what happens to the temperature? It goes down. That's even the opposite thing of what he's trying to say. And we'll just end with a little disclaimer here. The University of California formal definition of WTF, the one I have to give you is Wednesday, Thursday, Friday. So not everybody gets it. So we are going to just summarize that here and wrap up. I'll take a few questions prior to the exam. Here is a complicated three-dimensional graph squished on to 2 dimensions. I have the names of the levels of the atmosphere: the troposphere, the stratosphere, and the mesosphere. The altitude going up here in kilometers. So 70 kilometers, this is the altitude on this axis. Along this axis, the pressure, and along this axis, the temperature. And the ozone layer there in the low stratosphere, high troposphere. This is the plot of the pressure in blue. So as you go up the atmosphere, the pressure drops. It starts at 1 atmosphere and drops down. That's the axis of pressure. And by the time you're up here, 70 kilometers above the atmosphere, you're at space and you're getting down to 0. This is where Richard Branson and the other guy, Jeff Bezos, went because they're billionaires. And they can do it because they don't pay any taxes. If they had to pay taxes, they wouldn't be able to afford to go to space. The temperature, and now we understand that this is also decreasing temperature. The temperature decreases due to adiabatic expansion. And then in the stratosphere, it actually gets warmer again. And this is due to some of this action, chemical reactions happening in the atmosphere. And then, of course, as you go higher up and get towards space, the temperature is going to drop dramatically again. So there it is, our understanding of the atmosphere and weather. We're able to understand all of it because we understand thermodynamics, adiabatic processes, we understand equilibria, we understand the properties of gases and phases. And we are now, in this class, all better equipped to do a weather forecast than that guy was. It's funny, though, when you come to Berkeley, and many of you are here, the weather forecasts are extremely boring because we're here in California and we have no weather. It's always the same. So when I came here from California, I was just startled. I'm from Michigan. I was startled that every day was the same and you could just wear the same clothes year round. So the weather forecast is always the same. You turn it on the radio and they say, fog forming in the morning, turning partly cloudy by midday, temperatures at the coast 60 to 70, temperatures inland 70 to 90. You understand? They could put it on a loop. They don't even need a meteorologist. Just push the weather play button and just play that loop every day. So we'll end there, and I'll take some questions for the exam if you have any. So go ahead and I didn't turn on my Zoom, but Andrew, you can just turn your speaker on, and we'll come out of the breakout rooms. You can ask questions directly with your microphone. You can type questions into the chat on YouTube. If you happen to be here in person, you can just ask me. So go ahead. What do you guys have out there that's a burning question? And these are chemistry questions. Administrative questions, of course, ask your GSIs offline. Anything coming in? You guys wanted me here. The vote was more than, or at least half of us wanted me here. Sophia, you didn't care. I looked at the chat stream and you were voting 0, 0, 0, 0, 0. Did not want to come, but she came in person anyway. The Zoom, the iClicker was anonymous, but we had a lot of people saying that they wanted to come. Okay, we have a question. The question is, can we talk about an electric dipole moment just briefly? And it is so important. You're going to see this on the exam. So a good question. Let's review that briefly. The key thing to remember is all bonds, and you can take this to the bank, essentially. All bonds have some polarity. Polarity, poles, a gradient, a plus and a minus, a north and a south. There's some polar aspect to this. That polarity arises from the electronegativity difference. So there's a difference in electronegativity if all elements have a slightly different electronegativity. So all bonds are probably going to be somewhat polar. Sometimes the electronegativity is so similar. For instance, carbon-hydrogen bonds, that's heteronuclear, but those are very similar electronegativities. So there's not much of a polarity there. But if you talk about HCl, now chlorine, very much more electronegative. And how do I just remember that? I know something about the structure of the periodic table, and electronegativities are low here, and they increase as I go up the periodic table. So that's a periodic trend that we're responsible for. So I know Cl being up here, hydrogen being over here, there's an electronegativity difference. This is the more electronegative ion or element. And the definition of electronegativity literally comes from measuring bond polarities. We go from this to this. So the way these things, this isn't something you can calculate with a mathematical expression. This is something you go and you measure the polarity of bonds, and you compare all the different elements, and then you say, oh, well, when chlorine bonds with hydrogen, there's a polarity, there's a negative sign, partial negative charge at the chlorine. It's a polar bond, it's relatively strong dipole. Chlorine is much more electronegative than hydrogen. And you start doing that with all the pairs on the periodic table, and you work out what this is. Linus Pauling, we use the Pauling scale. Did he win the Nobel Prize? I don't think he won the Nobel Prize. This is just something else he did. I forget. But anyway, electronegativity. This is the more electronegative element. And that means the electron cloud is favored. There's more amplitude when you form that molecular orbital. There's more amplitude over here. So there's a little bit of negative charge. Electrons spending more time over here, if you like. Higher amplitude of the wave function over here than over here. So there's a partial, this little delta means partial, not a full negative charge over here. A fraction of negative charge here, a fraction of a positive charge here. And that is what we call any charge separation, is called a dipole. So all dipole means is charge separation. It's hard to attain. It's hard to attain charge separations. Charges don't want to be separated. Pluses attract minuses. That's the low energy state. So there has to be some potential energy state that involving these two nuclei and their wave functions as they overlap to form molecular orbitals. There has to be something that stabilizes that state that you wouldn't normally find. It's tiny, it's a fraction of a charge, but it's measurable. And we draw a vector. It's a vector quantity. So it has not just magnitude, the magnitude of the charge difference, it has a direction. And we draw it like that, a vector from the positive to the negative side. So the dipole moment is a vector. It has magnitude, and that's the electronegativity difference. And it has a direction, which is from plus to minus. And we're saying pretty much every bond has one, because it's kind of rare. Carbon hydrogen is such a common bond, so, and that one's not very polar, but every bond has a little bit of polarity, a little bit of a dipole moment. So, and you can detect it if you put this is, I mean, I wish we could do this experiment. If you just take a charged rod, so if you take a piece of plastic and you rub, the classic way to do this is you take cat fur. A little morbid, I guess. Back in the day, it wasn't so morbid. You take any kind of cloth, will kind of do this, and you rub it against plastic. That some of the electrons from the fabric are rubbed off onto the plastic, and that becomes charged. And if you have a stream of water, which has a permanent dipole moment, if you have a stream of water and you bring that rod close to it, the stream of water, if it's thin enough stream, will deflect towards that rod, because the waters have these, and the little positive ends of those dipoles, all the water orients, and so much of it orients with their little positive charges pacing towards that negative, that the whole stream of water deflects. Do that at home. Amaze your friends, fool your enemies with that. You need a very thin stream though, so you kind of have to do it almost with a burette, a stream of, you know, less than or about a millimeter maybe in diameter stream of water. So that's basically the idea. Those are the things you have to know. Last thing you have to know is, since it's a vector quantity, Since it's a vector quantity, molecules, all the individual dipoles in the molecules could cancel out to 0, and a molecule might not have a dipole moment itself if it's very symmetric. But that's also pretty rare. So many molecules have dipole moments, and one of the reasons we talk about dipole moments is because this is a question I can ask you: what is the structure of carbon dioxide in water? Because we know how to do Lewis dot structures in VSEPR, and we can say that one's linear, this one's bent. And if this one's bent, then those, oops. Start again. Then those little dipole moments, there's partial plus on the hydrogens and partial minus on the oxygen. So those little dipoles point like that, and those two add up as vectors to form a permanent dipole moment on the water molecule. And that little positive end is what points towards the negatively charged rod. It's also why water heats up in a microwave. We talked about that. This plus and minus is affected by an oscillating electric field that is an electromagnetic wave. So that's a plus minus oscillating field, and that gets that baby rotating. And that rotation translates to more motion in the sample and heat, and it happens very fast in a microwave oven. Well, that was about all you need to ever probably hear about dipole moments. Did that satisfy you? Mysterious, what's the person's name? Hannah. Give us a thumbs up if that helped you.
We have our office hour MVP, Lucille. The question: what is the difference between STP and standard state? When do you use each one?
Lucille asks, what's the difference between STP, standard temperature and pressure, and standard state? I love that question. Leo said Lucille's the MVP of office hours. She's always got a question. It's always a good one. STP, standard temperature. You can see why I'm awful on a chalkboard. Standard temperature and pressure, STP, and standard state. Because I keep saying that, and it bugs the crap out of you. You probably even like have an actual physical nervous reaction when you see it on the exam. Oh my God, it's standard state. I'm sorry. It's so simple. All this means is that all pressures and all concentrations are one. It's not a common state. It's an uncommon state. It's the reference state. We have to choose a reference, remember. We have to kind of choose a 0 for where we compare all our state functions. So this is a reference. State, not one that normally exists. You compare everything to that one thing, because if you're going to look at things, you have to compare. You got to be fair. You got to compare everybody to one state. So it's the standard state. And remember, we said this can be, it's a function of temperature. We can have standard states because all it is all the pressures and all the concentrations are one. We could talk about it at a number of temperatures. In general, when they give you the tables, it is at 25 degrees, but that doesn't mean you can talk about the standard state at other temperatures. And we did that today. We said, what's the standard state at 100 degrees C? Well, it's always 1 atmosphere and 1 molar. Standard temperature and pressure is just room. It's just the conditions you normally get. So standard temperature is 298 K and 1 atmosphere. So while this is extremely uncommon, this is extremely common. It's also kind of a reference, standard temperature and pressure. So we can all say, we're all working at standard temperature and pressure. So if I compare my reactions to your reactions, I did mine at standard temperature and pressure. I'm sure you did yours at standard temperature and pressure because it's room temperature and room pressure. Okay? Other things? What does the formal charge say? I'm really glad. Who asked that one? Austin. I'm kind of glad Austin asks. Austin asks. Let's go to the emails. Austin asks, what does formal charge say about a molecule? Nothing. I shouldn't say nothing. Formal charge is this construct that we come up with to evaluate the quality of our Lewis structures. So it's something we apply to a Lewis structure. And you know how we do it? We do it that silly way where we divide up the electrons as if they were all perfectly shared. Not reality at all. So formal charge is simply a metric by which we measure the quality of our Lewis structures. It does generally, though, and it always, the formal charges on all the atoms do add up to the charge on the ion, if it's an ion, or 0 if it's neutral. And we say formal charges should be on more electronegative elements, but that's, again, an artificial constraint that we put on it to judge the quality of our Lewis structures. So short answer, nothing. Just a metric that we do, a little accounting we do to compare one Lewis structure to another Lewis structure. Other things? Yes? Amanda who? Start with an A? Yeah. Amanda, why do you have any questions? You know I love you, Amanda. For everyone, Amanda got all the points on the last midterm. We love you, Amanda. Thank you for asking. Go ahead.
So for her first question, in a PV plot for a real gas, how does the volume dramatically increase at a constant pressure during condensation? Wouldn't the liquid forming leave less space in the container for the gas to occupy?
Yes. I'm not positive what the question is because you answered it. We were drawing, I think this is what Amanda's asking, is there's this discontinuity. Is this what a PV diagram? So here's a PV diagram, and this is some substance. And we said this discontinuity happens here, where suddenly you get free compression. So here you had to pay for your compression. The pressure went up. So let's squeeze to make it go more. If you have a sample and you're squeezing it and suddenly you don't have to squeeze anymore, you can squeeze it without exerting any more pressure. So the volume decreases at constant pressure. That is because the particles are leaving the gas phase. I think you were talking about it in the other direction, but that's the direction to think about it in. And remember, this is an isotherm. That's one temperature where that's occurring. I hope that helps. Next question.
Next question is, how does the number of electrons an atom have affect the bond enthalpy or bond dissociation energy?
How does the question, I think, is how does the number of electrons that a molecule, an atom have affect the bond enthalpy, bond dissociation energy? Well, we can see, Amanda, the reason you get lots of points is you have good questions. You're thinking about these things in a very deep way. So the question is, there's lots of electrons around, and can I correlate somehow the number of electrons, the association of the electrons with the bond enthalpy? Well, short and sweet answer for the exam, yes, because we take electrons around atoms and we put them in molecular orbitals and we calculate a bond order. Higher the bond order, the higher the stronger the bond, the greater the bond enthalpy. In the larger sense, you have these wave functions overlapping, and can I say, how does the distribution of electrons, or does the number of electrons in those standing wave functions affect the enthalpy? And that's a slightly more complicated answer, but it kind of boils down to the same thing. You add your atomic orbitals together and you get molecular orbitals, and you find some of them are unfavorable and some of the electron distributions are unfavorable. So if you have too many electrons, then you start forming unfavorable standing waves, orbitals, and that decreases your bond enthalpy. So there's the number matters. There's a good number, but if you have too many, you start to get worse. Okay. All right. Well, good. Oh, there's more. Fantastic.
Okay, so Daniel has a question about, I'm guessing it was from the water stream and the example, and he mentioned that, I'm not entirely sure what he's asking, but he mentioned that even without DI water, it's minerals responsible.
Oh, no, I see. Oh, so Daniel has a good question. So I described this experiment, and I'll kind of draw a picture. So say I have a burette here, and it's full of water. So I can make a stream of water, a very thin stream of water come out there. If I take and put next to that a charged rod, that's a source of charge, then that water deflects around it. It's cool. It's surprising. You don't expect it to happen. If you do it with propanol or something that doesn't have a strong permanent dipole moment, nothing happens. So that's due to the dipole moment, and now we know it's due to the fact that the water molecules are lining up. There's the minus and plus side of the molecule. They're lining up and then being attracted to that. And Daniel's question, will that happen with deionized water with no ions, the mineral content? So TDS, total dissolved salts, in the parts per billion. Where's that coming from? Whose speaker's on? Oh, Daniel, you're asking, oh yeah, you want to talk? Go ahead. Go ahead, we hear you. So yeah, so in your you can turn the speaker off. So yeah, Daniel, what you're saying is, yeah, indeed, this has to be very, very, very thin, and it has to be thinner the more deionized you are, the lower your dissolved salts are. Certainly, if you had an ion content in there or a metal content in there, and that kind of depends on what your what this charge source is. So just a myriad of factors. But I will tell you, I will do that. Maybe I'll just have Karen do this. I'll bring it up. Some deionized water. We'll have her certify it. So yes, tiny stream. And that's just hard to achieve. So if you're saying, can I do this in my kitchen with my sink and the stream of water coming out of my faucet? Probably not. there's too much mass. There's not enough attractive force to deflect that water. So super tiny stream, not a lot of mass density along the stream, so that will deflect, and it's the dipole strength of the fluid matters. And you can take different dipole strength fluids and see a different deflection. Okay. Yes.
Another question from Lucille. So why is the pi bond in N2 lower in energy than the sigma bond?
Lucille is asking about molecular orbital diagrams, and what we did is sometimes we write the molecular orbital diagrams like this, and sometimes we write them like this. So we have an interchange of, so these are pi's and these are sigmas, and there's an interchange of sigma and pi energy levels. The short and reassuring, well, a short and reassuring fact is you do not have to know that. It is a rather sophisticated result of the molecular orbital theory. So something comforting is I will always give you this diagram. You won't have to generate it. So you'll be given this, and you'll have the ordering of them. You may know, but there's some intuition about why it happens. Why does the sigma bond drop in energy as you get to the slightly larger atoms? Well, they're getting farther apart, and the pi interaction is better than is lower energy than the sigma because of the geometry of the larger going to larger atoms. So there's some intuition there. So these things that look like the abs of a trim person. So of course, if I'm not allowed to take off my shirt. Sorry, the University of California doesn't let me do that either. But you would see, ripped energy levels here. In fact, a 9-pack. There's just two people, me and Lego Batman, have the 9-pack rather than the 6. Okay, other questions?
Amanda has a question about molecular orbital diagrams as well. So she said that going back to the number of electrons affecting bond enthalpy, what if there are no electrons in the molecular orbital? I'm guessing. I think she also said no. No, never mind. I guess you figured that out.
Yeah. The situation where there are no electrons to put in here would be rare. The situation where a bond doesn't form isn't because you don't have enough electrons. It's there are too many electrons in anti-bonding orbitals. So there are too many electrons destabilizing the bond. So it's not the fact that there aren't any, it's the destabilizing ones in the pi star and sigma star antibonding orbitals. Other things? All right, wonderful, guys. We also do a little review on Monday. So, Lillian.
How do you know which atoms have an expanded octet?
So the question is, how do we know which atoms are allowed to expand their octet? Short answer, if you count up all the valence electrons and there are too many, expand the octet. Okay. The longer answer is when the d orbitals come into play. So as you go farther down the rows of the periodic table, that becomes possible. So as you get over here into this side of the periodic table, the high 3 and 4 quantum levels, then the d orbitals are about the same energy as the s orbitals, as you know, and that allows that expansion of the octet. But in general, expand at will. Other things? All right, wonderful guys. Have a great weekend. We'll see you Monday.